Okay, so in this one we're going to find the volume of the region under 4x squared plus 4y squared plus z equals 4, and above this monster, z plus 1 is equal to the square of x squared plus y squared. All right, so we've got some not just quadratic, but actually like fourth order equation defining this surface. So that's not a familiar one. Let's see. So first thoughts. Both of these seem to translate nicely into cylindrical about the vertical, about the z-axis. So I've got those two. If I tried to set them up in spherical, it might be kind of a hairy mess. So let's see. So on this side, we would have like 4 rho squared sine squared phi plus rho cosine phi equals 4. That looks moderately painful. And then over here, oh my god, it's even worse, right? So it would be some, on the right side, we're going to have rho squared sine, we're going to have rho to the 4th sine to the 4th phi, and rho cosine phi plus 1. And none of that looks pretty. Okay, so I'm just going to say let's not do spherical. Okay, so what does this thing even look like now? So for the, let's say z equals 4 minus 4r squared, or 1 minus r squared. Well, 1 minus r squared, that actually looks like a paraboloid. And so 1 minus r squared would be the one that has, that we're at height 1 up here. But now we're multiplying it by 4, so it's going to be at height 4. And then this is still going to be here at z equals 0. What about the other shape? So we've got, solving that equation, we've got, let's see, z is equal to r to the 4th minus 1. So x to the, let's see, so if we've got x squared, let's do x squared, x cubed, and then like x to the 4th going on like that, then what this would look like is a surface of revolution of that x to the 4th one. So it's going to be something coming up flat on the bottom and then real sharp at the sides, kind of like this. And so kind of like a paraboloid, but like with a blunter bottom, I guess. It's still opening in the positive direction because this guy is positive, unlike this one, which is opening downward because it's negative. So these things are going to intersect to form some sort of egg shape kind of a thing. And where do they intersect? Well, let's see. So we've got, I guess, just by staring at it when I realized what I just did. I drew this at the wrong height. It's actually down here because of the minus 1 part. Aha, okay. And I was just noticing when I stared at it that both equations have z equal to 0 when r is equal to 1. So when we put r equals 1, this becomes 0 and this becomes 0, so we get z equals 0. So that tells me that they intersect in the circle of radius 1 right here. All right, so there's our eggy. So let me draw a slightly better. Something like this. Okay, better, yeah, maybe not. All right, So let's set this sucker up. So we're going to be doing this one with cylindrical coordinates around the z-axis. So let's see, it's a full spin all the way around. So we have 0 to 2 pi for our theta. And then I'm going to do this one dz, dr, d theta, because that means that I'm going to be setting up the z bounds here in the form z equals and then like some function of r in it, right? And I would, going back to this equation here, I've already got that set up. Or this one right here. And if I were to do it the other way around, so in other words, if I did dr, dz, d theta, then I would have to deal with a fourth root, and that doesn't sound like as much fun to me. So let's see, we've got on the bottom, now the bottom is given by the blunt part of the egg, that's the part with the fourth. So that's going to be going from r to the fourth minus 1 up to the top surface, which is given by our paraboloid, 4 minus 4r squared. Okay, and then the radius is saying how many of these egg to paraboloid, egg to paraboloid, egg to the paraboloid stripes do we have? Well, we include the axis here, so we start with r equals 0, and we go all the way out to this last one right here where they intersect, which we just figured out was r equals 1. So it's going to be 1. And we are integrating volume, so our only integrand is r coming from the Jacobian. Okay, ready to go, and yeah, let's do it. Okay, so there's no thetas in there, so we can Fubinate the theta integral as 2 pi, and then we have integral from 0 to 1, and then we are integrating z from a to b, so it's just going to be the difference of those guys. So we have 4 minus 4r squared minus r to the fourth minus 1 times r dr as our inner integral. And now it's just some snarby polynomial, but I guess it's not even a bad one. So let's see, so we've got 2 pi integral from 0 to 1, and I'll multiply out some stuff and get like 5r minus 4r cubed minus r to the fifth. Yeah, combine those two constant terms, dr. And so then this is going to be 2 pi evaluated from 0 to 1. So we integrate the r to r squared over 2. And that becomes r to the fourth. The 4's cancel. And then we have r to the sixth over 6. And this is 0 to 1. And so the r's are all just replaced with 1s, and each of these functions vanishes at 0. So we have 2 pi times 5 halves minus 1 minus 1/6. And collecting all that together, we get 8 pi over 3, if I did the arithmetic right. Oops. And there's our answer.